welcome to Electromatic Spectrum. I'm Laura Lewis. So we're talking about the EM spectrum or the electromagnetic spectrum today. It's going back to the beginning here, sliding back. That's what we'll be talking about today. So this is for all exam specifications, so OCR, EdXL, AQA, so on. Okay, you could be asked any of these things, any of those categories. Okay, so just put full screen now. Make sure. Yes, I'm still screen sharing. Okay, let's make sure. Okay, so let's have a summary then. Okay, so next slide. So overview number 1. So an overview of the electromagnetic radiation from gamma to radio waves. Number 2, an understanding of the uses of the parts of the EM spectrum. And number 3, a discussion of the dangers of different parts of the electromagnetic spectrum. Probably sick of the word electromagnetic already by now. I say EM quite a lot, just to shorten it up. You don't have to keep saying electromagnetic. Okay, so what does it actually mean to be electromagnetic? Okay, so all waves on the EM spectrum, from gamma to radio, they're all transverse. So that means that the direction of their travel is at right angles or perpendicular to the way they vibrate. Okay, so kind of like how you draw a wave. It's kind of, so why are they called EM though? We've got a wave, but why are they called EM or electromagnetic? Because they're made two components, the electric component and magnetic component. You won't have to know this at GCSE, but I'm just showing you where the word electromagnetic comes from. Okay, so you get into something called polarization when you get to A-level physics. So in a vacuum, so it's completely empty space, all electromagnetic waves travel at the same speed, so 300,000 kilometers a second. But in science, we like to write things in standard form, only meters per second. So it's 3 times 10 to the 8 meters per second. Okay, so that's only in empty space, so vacuum. So it's because there's no particles to get in the way. Okay, so if this is like, if the wave or the ray was traveling through glass or even air, it does actually slow it down a bit. So you can't see with our eyes, so it does that. But say if you're a ray of light going from the sun to the earth, through the empty space between the sun and the earth, that you can travel at a nice high speed of 3 times 10 to the 8 meters per second, but going into the Earth's atmosphere, actually you would slow down, and going into a window, you slow down even more. But yeah, it's imperceptible to our eyes, but it does actually slow down through non-empty space. So overview, there's going to be lots of overview slides, okay, because lots of things you need to see compared to each other. So the longest wavelengths and the lowest frequencies and the lowest energy, okay. So at the radio, so 1 meter and above, so this is all the meters, 1 meter and above radio, so they can go from 1 meter up to several kilometers. Radio. Microwave, 1 to 10 to the minus 3, so that's centimeters. Infrared, 10 to the minus 3, so millimeters. Okay, to micrometers. Visible is very tiny, we wouldn't be able to see that with our eyes, like the actual individual wavelength. Obviously you can see visible with our eyes, but that's so small we can't see it. Ultraviolet, okay, even smaller. So the next slide compares things, we'll see in a moment. X-ray, small, gamma ray, tiny. So this end gamma ray, high frequency, high energy, small wavelength. You can see here. Radio end, so one extreme to another. Low frequency, low energy, long wavelength. This is a nice slide. It encompasses quite a lot of bits of science actually at this slide. In one go. So yeah, radio can be for the approximate scale of buildings, okay, human wavelength, so we'd kind of be the same size as a radio wave. Okay, insects and butterflies into microwave, so centimeters, so it's just like a nice thing, isn't it? Infrared, getting to just about be able to sort of see the wavelength size. Visible, okay, so protozoans, so things you might see in biology class under a microscope. At this point it gets very interesting, because if the object is actually smaller than the speed, so it's smaller than the wavelength of light, we wouldn't see it with our eyes. Like molecules, they're smaller than visible, so we actually can't see them with a light microscope. Okay, X-ray, smaller atom size, definitely couldn't see that. And gamma ray, atomic nuclei, so they're very, very short wavelength. Frequency, okay, you can see here. And temperature at which objects most intense wavelength emitted. Okay, so this means that the colour of an object, the way if it's glowing, that is, if an object is glowing, the colour of it actually tells us what temperature it's glowing at. So our sun is about 6,000 Kelvin, about 5,800 degrees Celsius. So it glows kind of here. So actually that's why we see it as yellow, because it's glowing here-ish. Okay? Some stars are blue because they're much hotter than our sun. They go at 10 million degrees Kelvin Celsius. Humans, I mean, anything that's got a temperature actually does emit emits EM spectrum light. We actually go in the infrared, humans, so we kind of be glowing here. We can't see it otherwise, so we would be glowing. Okay, so it's a bit of a summary of that. Okay, what we've just talked about. So radio, microwave, infrared. Humans, we can't see it. Some animals can see infrared, like snakes. Wavelengths approximately 0.5 to 10 to the -6, so micrometers. We can see the visible, okay, and wavelengths approximately 10 to the -6 to the -12, not visible. So it's kind of a good idea to call it visible because it's visible light. Okay, the sun, okay, gives out mostly the radiation in this part of the spectrum, the visible part. It does give out all the others to a much less extent, but mostly in the visible part. So humans and most other animals have adapted and evolved so we can actually make use of this part of the spectrum that the sun gives out most. It's funny to think that we've evolved because of what the sun gives out. Okay, so if we orbited around a different star, life developed around another star in our galaxy, it could develop a different way of seeing. You could see in the infrared or ultraviolet, probably, depending on what the star gave out. Interesting to think about. Okay, sorry. We're talking all day. The electromagnetic spectrum. Okay, so this is an overview of the uses of the electromagnetic spectrum. So we'll go through each in detail, just a few slides. So radio, probably know radio, like and TV broadcasts, like communications, mobile phones often use radio. Microwave, cooking food, radar. Infrared, cooking food, remote controls, thermal cameras, visible light. Yeah, eyesight. Yeah, sight, illumination. People forget to write that in exams. Illumination cameras, ultraviolet, tanning beds, black lights. We'll talk about that in a moment. X-ray, medical imaging. It's probably the easiest question you get. What an X-ray for? And gamma. So that's gamma. That letter. Gamma rays, medical imaging, radiotherapy, and sterilisation. Okay, let's get into detail. So radio waves. So your television. Okay, when it receives broadcasts. Okay. From a satellite dish, where you've got satellite, it's a radio wave. Okay, so like Sky TV will be a radio wave. Your phone, okay, so when you call someone, that's you emitting radio waves from your phone, and you receive radio waves from someone else. Okay, usually a mobile phone mast will be in the middle, but you'll receive radio waves. The reason why we use radio waves communication is that they're very long wavelengths. Obviously they're harmless to humans, but also it's because they bounce around valleys and you get a good reception even if you in a mountainous area and you're at the bottom, you live at the bottom here, is that the radio waves will diffract around the mountainous area and you'll still receive a signal. Okay, you won't lose your signal. Okay, microwaves. So a little bit higher energy. So your microwave oven in your kitchen uses microwaves, believe it or not. You might have guessed that. If you're heating up food, okay, in a microwave, you're using basically like light energy, but in a different format to actually heat up your food. So how it actually works is microwaves actually cause water molecules to vibrate in your food. So don't put anything in there that's dry, especially chocolate. Do not put chocolate in there because it'll just burn it. Well, I haven't done it before, it comes from experience. But yeah, don't put anything dry in a microwave, it'll just burn it. Okay, even pizza I don't think is that good to put in a microwave, but it's not dangerous, it just doesn't taste as nice. So satellites in the atmosphere, they use a lot of microwave because the microwaves can get through the Earth's atmosphere. And also on aeroplanes, they use microwaves to bounce off objects to see if they're there. And they bounce it off and they receive a signal back. Okay, so that's a radar there. Infrared. So yeah, this is the frequency that some animals like snakes can see at. So infrared will be 300 to 400 terahertz. Okay, so used in ovens just for cooking food. So 1mm to 740 nanometers. The cooking food remote control, so your remote control will use infrared, like a little emitter, and that's how you turn television over or turn television on. It's using a remote control. So this will, it only works in line of sight as well. So you probably know that you have to put your arm up or above your head or something to turn television on, because it only works in line of sight. You might think, oh, I've got a game controller, like a PlayStation 4 or something controller that works without line of sight, because it's probably using Wi-Fi, it's using radio waves that could diffract. Infrared doesn't really diffract or anything. Also, thermal imaging cameras. Okay, so you see sort of like the heat that people are emitting. See that mostly it's in their face and their hands. Is emitting most of the heat there. Okay, visible light. People again always forget about this one. So yeah, our eyes. Okay, so our eyes are sensitive to visible light. We can see. So also lamps will emit visible light. Obviously, we can see it as well. And cameras. So they're always good answers. So eyesight, illumination or lights, and cameras. The ultraviolet. Okay, ultraviolet. So the sun emits ultraviolet light. So you may have heard the ultraviolet first of all from like a sunscreen advert, which I didn't think, probably heard it from the protects against UV radiation. The sun emits ultraviolet light, and we don't want to get too much of that. We get sunburn and cell mutations and things. We'll talk about the dangers a bit later. So tanning beds, they use UV radiation, okay, to give people a tan. Not very safe, okay, so I wouldn't recommend people do that. Black lights at parties and things, they use a type of UV light, and that's where you see people's clothes are fluorescent, especially if you're something white. Okay, your clothes will fluoresce. Okay, so it looks like you're glowing, but it's ultraviolet radiation that's being sort of bounced off you, affected off you. Also, if you work in a shop and check banknotes, okay, so a real banknote, like not a fake one, will have like a little 20 sign actually printed into it, obviously with a special technique that only that if you put it under a black light, so there's like a bulb in it, under a black light, that it will show up. So if someone forges, and they're very, very unlikely to have the technology that the Bank of England has to actually put that in, and you can tell it's a fake or a real banknote. Okay. X-rays, probably this is one everyone knows most about, isn't it? X-rays. So medical imaging. So two types of medical imaging for X-rays. So you've got the standard type, okay, so which most people don't realise is that the actual film this is on, so it's like a photographic film that actually it's originally white, okay, so it's originally white, and the X-rays turn it darker. Okay, I saw a question in the exam the other day about that, about a radiation badge somebody will so that someone wears working in a hospital, and is that if they're exposed to radiation or X-rays, the badge will actually turn darker. Okay, so but the white areas are the parts where the X-rays have actually been blocked. Okay, so the bones are where the X-rays are blocked, and the dark bits where the X-rays have actually penetrated through. So it's not really an X-ray is not really useful to look at things like soft tissues like skin, kidneys, hearts, things like that. It's good to look at bones, but not really the soft tissues of your body. That's why I use other imaging for that. So yeah, you can see the bones have blocked it out. That's I focus on that because I saw a question about that the other day. Lots of students didn't really realise that actually the X-rays cause that photographic film to become dark. Okay, so this is a CT scanner. So it stands for computerized tomography scanner. A person goes through here. It's very open, so it's not closed in. Goes through the scanner, and a three-dimensional X-ray is made of the body. So some conditions can be picked up with a CT scanner. Okay. So yeah, medical imaging is the general answer to X-rays. So gamma rays are known as the most dangerous, but also one of the most useful ones to certain types of medical applications. So you have gamma imaging. It produces something very like an X-ray, a gamma imager. So gamma is not too different from an X-ray. Okay, but you can get gamma imaging for medical imaging. Gamma is also used for sterilising equipment. So if you've been to the dentist and seen them come in with a tray of instruments, okay, it's been put through like a sort of sterilisation. It's called sterilisation oven. They're sort of put in a bag, and gamma radiation is actually penetrated into the bag and kills all the bacteria and viruses. Okay, that's on the equipment there, and it's obviously safe to use. So as soon as obviously that they're done with you and then the dentist, they'll take it away and they'll put it in the bag for the next person. Okay, that's all sterilised, so it's safe. Also, another thing, this is radiotherapy. So this is one of the newer sort of versions of it. You have 3 machines, okay, and they can revolve round, and what they can do is to actually target a source of cancerous cells in the body. So if you may have a tumour sort of here, you can actually target them, move them around. It's like a sort of a grid on the person in light. So yeah, it's not drawn on, it's a light that's above them. There's sort of you actually target it, so it will be focused on the cancerous cells and the tumour, and not kill too many healthy cells. There's a reason the gamma radiation affects cancerous cells more than healthy cells, is that cancerous cells are dividing very quickly, and any cells that are dividing very quickly are very prone to radiation damage. And actually, in that case, we want to damage those cells, cancerous cells, to stop them dividing too quickly and hopefully not damaging the healthy cells around it. Okay, so dangers of the electromagnetic spectrum. So yeah, some of the benefits, but we haven't talked about the dangers quite yet. So the higher the frequency, the more dangerous it is. The gamma rays, they can treat cancer, but also gamma rays can cause cancer. And it's kind of ironic. So gamma rays can actually lead to cell mutation by damaging the DNA of the cell. Okay, the gamma rays can treat cancer, and they can also cause cancer. Unfortunately, they actually damage the DNA of the cell. X-rays, again, cause cell mutations, because you have to limit the amount of X-rays you have per year. If people work in a medical facility, they have to actually either stand behind screens that protect them from rays, or actually go out of the room and they take the X-rays. You might see someone suddenly go out of the room and they take your X-ray, because when it's safe for you to have one, they have to sort of work there all day. Okay, ultraviolet, yeah, again, this is why I said don't do the sunbeds, everyone. Skin cancers, okay, because the sun can do that, but also sunbeds can do that. So always wear sunscreen in the sun, and you can lead to skin cancers. Visible light, again, it's like no known dangers of it, but yeah, you don't look at a bright object like the sun or anything that emits really bright light, or you could damage your eyes. Okay, common sense involved there. Infrared, sunburn, burns, yeah, skin burns caused by infrared. Microwaves, few, there's one that obviously you wouldn't want to obviously put your hand in a microwave oven. Obviously you can't really do that, but yeah, don't try and do it either, okay, because it can lead to internal heating, internal burns. Again, so it's unlikely you'll see that, but obviously internal heating, internal burns in microwaves. TV or radio, yeah, no known dangers for that. It's very long wave, it's very low energy. Not many dangers surrounding that. So, sort of an overview. So, ultraviolet, yeah, sunburn, skin cancers, damage to skin, ultraviolet radiation, damage to eyes as well. So that's another one actually. UV can cause damage to your eyes, so wear sunglasses as well, because it can damage your eyes over time. Some people are quite prone to it, damage to UV radiation, their eyes. So with this one, so X-rays and gamma rays. So what this is showing that it can mutate DNA. So that's a DNA mutating it. And if DNA is mutated, normal cells can actually become sort of damaged, and they don't know when to stop dividing. And that's what a tumour is. It's damage to DNA, and the cells kind of go a bit rogue, and they don't know when to stop dividing. Okay, so that's the dangers. So let's look at an overview. So we looked at an overview of the electromagnetic radiation from gamma to radio waves. So let's go through the individual slides. Sort of each one's got a different use. So understanding of uses of the electromagnetic spectrum. We just did that about different uses. Discussion of the dangers of different parts of the EM spectrum. So yeah, it's good to look at overviews like this. Like this slide is a good overview about looking at the key points like low frequency, low energy for radio, gamma rays, high frequency, high energy. It's good to remember the order of them as well. How I always did it was look at visible. It's the rainbow, isn't it? Okay, so that's what it's a rainbow. So it's red to violet. The ultraviolet sits next to violet, infrared next to red. So you've got to start there. Okay, radio's longest, gamma ray's shortest, and you've only got two more to remember than that: microwave and X-ray. Okay, so X-ray, yeah, a bit more close to a gamma ray. The infrared, more close to a microwave. So that's how I remembered it. I didn't have a mnemonic to remember it, but I remembered it like that. Okay, approximate sizes. Again, you won't need to know exact numbers, but you need to know compared to each other. Yeah, only visible light is visible to us. So it's got a good name. This is a good oval slide. You've sort of like paused it and then just copied it, okay, somewhere. It's look at the applications and the overall uses and the dangers on this slide. So let's look at the overall dangers. So thank you for watching the video. I hope to see you in another class. Thank you. Let's get in that there. Thank you. Goodbye.